think everything's working. Okay, cool. We should be live. Hopefully, as always, somebody will recognize our presence, and then we know that we exist. But at this point now, I feel like I trust it. So where in Australia are you located?
In Melbourne, so all the way down the bottom.
Yeah, yeah, yeah. And you apparently did a pretty good job with COVID. Where it's a bit of a disaster here in Canada still. We're on our like big third wave, lots of lockdowns, and you guys locked down pretty hard. And it looks like, I mean, like Melbourne was like the hotspot, right?
Yeah, that's right. Though I think how Melbourne was defining the hotspot wasn't like the rest of the world. So I think at worst it got to something like 700 cases a day. And at that point, I think there was like a 2 or 3 month lockdown where nobody could go, almost couldn't go outside.
Two or
And since
three
then, it's been
months
almost,
of being stuck inside. Yeah.
yeah,
So we never, I
it
mean,
was extreme.
yeah, we never locked down here on Vancouver Island, although other parts of Canada did. Like the West Coast, we were okay. But it's sort of been kind of a background and creeping up. But Ontario and Quebec have been pretty bad. Now the Maritimes are flaring. Oh, anyway, we got to get those vaccinations. And apparently
Yeah.
Americans are not using them up. So maybe they can start setting them to the rest of us now.
Yeah, right. It looks concerning now. It looked so promising before because it was
Yeah.
increasing so quickly. And then
Yeah.
now you see like the past few days.
Yeah, yeah, yeah. So people, I guess,
It's
just
a
like
shame.
everyone who wants one has had one. So anyway, who are you? What do you do?
So I'm Rebecca Lean. I'm an astroparticle physicist at the SLAC National Accelerator Laboratory at Stanford University. So I work on trying to understand what dark matter is. So dark matter is some mysterious sort of substance that makes up most of the matter of the universe, but we really have no idea what it is. So my research in particular focuses on thinking about new sorts of ways that we might be able to find dark matter using astrophysical systems or thinking about things in space, as well as actually doing some of the astrophysical data analysis as well.
And yeah, I love this. And so I saw your you had a paper on Archive a couple of, I guess, about a month ago or a few weeks ago, and I saw that and I'm like, yeah, because I love the idea of dark matter as this mystery. We know for sure that it's there, but we have
Right.
no idea what it is. And
Exactly.
and so to come up with clever ways to try to sort of suss out more of its properties, I think that's wonderful. So can you sort of set the landscape on, I guess, what we think dark matter is now? Like what's sort of the current scientific consensus for its mysterious properties?
Yeah, so the current consensus really at the moment is it could be so many different things. We really don't know. We know almost nothing about what it is. But a few of the really basic properties we at least think it probably does have is one, it doesn't interact with light, or it doesn't interact very much with light, if it does at all. Um, we think that it's mostly we say something that's cold, so it's not too like sort of fast moving. And the reason for this is just if we want to get the sort of the structure that we see in the universe today, it has to act a particular sort of way. And really, the main evidence that we have from dark matter only comes from its gravitational interactions. So we don't know if it even interacts with the visible matter, so the sort of stuff that we're made up of. It might not interact with visible matter at all. In which case it's going to be really hard to find it. We have to be extra creative about the ways we might find it if that's true.
Yeah.
But that's about it. I mean, the sort of mass the dark matter particle could have covers something like 80 orders of magnitude in mass. So it's just this massive, massive landscape of different things that it could be. And
80.
we don't know which one is the right answer.
So when you say 80 orders of magnitude, so you could have a particle that is a fraction of the mass of a electron, or you could have something that is intermediate mass black holes that are
Yeah. So,
built that are thousands of times the mass of the sun, and
right.
and dark matter could be any of those and anywhere in between.
Yeah, that's right. That's right. It could be some tiny, tiny little thing, or it could be some giant sort of, object that's a composite sort of object that's not
Right.
just a particle.
So
We don't know.
I guess you mentioned that we know that it is cold, And I think at this point we know that it's some kind of particle, that it's not that we just didn't understand gravity properly. Like,
Right. That's true. It also might not be just a particle. So there's a different type of sort of candidate people think about called primordial black holes. And these could be dark matter as well, but these things aren't just one particle. They're, these little sort of black holes that you get in the early universe. So there are different things it could be that's not just a particle. I think it's fair to say, though, that most of the community generally works on things that are particle-like.
and that and I know that idea of it being cold, and that rules out the neutrino. If dark matter was neutrinos, what would that look like in the universe?
So we have these excellent simulations that show us what the large scale structure of the universe kind of looks like. So for people that haven't seen it before, it just looks like kind of like a spider's web, where you just have webs of things that are kind of clustered around. And we know that if we simulate all the sort of matter we think is going to appear in the universe by putting some just initial conditions of how the early universe looks, and you have to put in some dark matter component to that simulation to get this sort of spider's web that comes out to look like the sort of structure that we see in the universe today. So when I say this structure, these are kind of like these filaments and bits and pieces that end up giving us the backbone to all of the galaxies and all the matter that does form. It kind of clumps together. And if you were to put in something like neutrinos as the sort of dark matter source in the early universe, you would just get all these structures wiped out. So you wouldn't get all these sort of filamenty sort of things forming. So the universe wouldn't look like what it does today if it was all in neutrinos.
And that's because the neutrinos are like moving close to the speed of light in all directions. They're not clumping up. They would just be this spray of particles in all directions.
Yeah, they're speedy. They're speedy.
Right. But I know there's one, and I'm not sure if this is your specialty, but I know there's one theorized flavor of neutrino that might be the answer, the sterile neutrinos.
Yeah, there's bits and pieces of things that you can do.
Right.
But yeah, overall, if you wanted to have it just be like the neutrinos that we know in the standard model, you need a lot more of them and they have to act kind of differently. Right. Once you start having these sterile neutrinos or other new things, they're not in the standard model, which is kind of like our current understanding of particle physics. They have to be new additional particles. So there's more of them and they do different sorts of things.
And of course, there's the possible unnerving potential that it's a combination of them, right? That it could be.
Yeah, sure. And I mean, I think that's also really pretty likely. If you look at the regular matter that we have like as people say, there's like a particle zoo of what makes up the visible matter. So we have like electrons, we have muons, we have protons, and inside that we have quarks. So really the visible matter is like a very rich sector. So there's no reason to think that dark matter is just one particle. It really could be, just like the visible matter. There's just lots and lots of different particles making up a bigger dark sector. And we really just don't know what the answer is in terms of one particle, lots of particles. Probably lots of particles would make sense.
Yeah, I mean, I think about the like even the search for the regular missing matter in the universe. Astronomers have been chipping away at that for decades now, and each time they're like, okay, we figured out that some of it is clouds of oxygen that we're seeing illuminated by quasar light from far away, and other parts of it are galactic halos that just weren't visible, and so on and so forth. And so you just sort of chip away and inch towards the final total. And so yeah, no, right. I'd never even thought about this possibility that dark matter is a whole bunch of things. But you're right. It's just of course it is. Of course it's not simple.
Also, yeah, definitely could be. Just to also add on the point that you were making, that we have, this missing matter in general, and people find, looking in astrophysics, like, oh, here's where more of the mass is that we didn't know about. Dark matter is also a little bit different in the sense that we know it's a type of matter. It's not just missing, it's different to the type of matter that we're all made up of. And we know this from looking at something called the cosmic microwave background. So this is just like relic radiation coming from the early universe. And if we look with our telescopes at this sort of radiation, we see it's really sort of patchy. And we can look at the information encoded in this to see that the way this sort of image is how the sort of physics is unfolding within this radiation, that there has to be another sort of matter to get this picture looking the way it does. So it doesn't interact very much, if at all. And yeah, it's totally different, not just something that's hiding off somewhere else, which is a type people have looked for before. But yeah, this one is something else altogether.
So your specialty then in astroparticle physics. So what have you been searching for?
So I've worked on a number of different things. One thing that I've been working on for the past few years is trying to understand this mysterious glow of high energy light coming from the center of our galaxy. So this is something called the galactic center excess, is what we call it in physics. And so it's just high energy gamma rays coming from the center, and we just don't know what causes it. And one really exciting possibility is that it could actually be dark matter annihilating. So the dark matter particles are, throwing themselves together and then releasing high energy sort of gamma rays. And so I've been trying to understand if dark matter really is behind this signal. So I mentioned earlier, we only know that dark matter exists from its gravitational interactions. We don't know if it interacts with the visible matter. But if this high energy light coming from the center of the galaxy is actually coming from dark matter, that would tell us dark matter is interacting with the visible sort of sector, because we got these gamma rays, this high energy light came out. That means dark matter does interact with our type of matter. Mm-hmm. So that would be really exciting. So I work on trying to understand what's going on there. I also more broadly lately have been thinking about how we can find dark matter in stars and planets. So what these signatures might look like. So the sort of the theoretical prediction for the signature, as well as looking at how these searches could actually be realized.
So let's start with the glow coming from the center of the galaxy. And I've been tracking this story for a long time, and sort of the main theory that I had heard a few years ago is that there was some kind of matter, antimatter annihilation going on at the galactic center, but that's recently been ruled out, right?
No, so it hasn't.
Oh, it hasn't.
It definitely hasn't been ruled out.
Okay.
So this has been, the story of this has really kind of gone back and forth. So at times physicists thought, oh, we understand it, it's ruled out. And then there have been new studies, a few of which I've worked on, that have shown actually it goes the other direction. So
right.
These studies are really hard to do. And the reason why the story kind of keeps flip-flopping back and forth is just that the center of the galaxy is really messy. So there's a lot of stuff in there, like there's a lot of regular matter. And, there's lots of old stars, there's lots of things we don't understand or can't model very well. So when we try and make a conclusion, usually the sort of error bars, like the uncertainties on the conclusions, are quite large. So it's hard to know for sure really what's happening, which is why some people sometimes think, oh, we ruled it out. And then it's like, no, you didn't rule it out. Maybe it actually still is dark matter. And I think the current status is it really could be dark matter.
Okay, because that does sort of sound a bit like the dinosaurs were killed by volcanoes. No, they were killed by an asteroid. No, they were killed by volcanoes. The sun will not consume the Earth when it goes as a red giant. Yes, it will consume the Earth when it goes as a red giant. So, okay, that's great. I should not put that one into the settled science, because I'm sure we worked on a story maybe 6 months ago going, yeah, it's definitely not. But we've actually covered this quite a bit. So at Universe Today. So then, okay. So what kind of process then, you talk about dark matter kind of annihilating, but as I understand, dark matter just doesn't have a cross section. It doesn't bump into each other. And there's lots of places where it could be doing that. Why would it be happening at the center of the galaxy?
Yeah, excellent questions. So the reason why you would expect the center of the galaxy is the dark matter density there is expected to be enormous. So we think that dark matter forms halos around galaxies, and because there's about 5 times more dark matter than regular matter in the universe, generally the halos are much bigger of dark matter. So there's this giant dark matter halo that goes around our galaxy. And if you think about the gravitational potential, which is, how much mass you end up getting in different places, if you just have, a big gravitational well, which our galaxy is, you end up getting just more of the mass being in the center. So if we do sort of simulations to look at how the dark matter might be distributed in this halo around our galaxy, it's really we think quite sharply sort of peaked towards the center. So if that's true, there are lots of dark matter particles there. Now your question is does dark matter interact with itself? So we think that dark matter doesn't interact strongly. It actually could. A lot of these things are not very well known. But if it does, the sort of interaction you have to have is actually quite weak in the center of the galaxy to get the right sort of intensity with as this signal that's been seen from the center. So assuming that dark matter has this dark matter as dark matter antiparticle, and they do interact, that is an assumption. If they do interact, then you would expect to see this light. And part of why it's actually really exciting is there are particular frameworks of classes of particle physics models that people think about for what dark matter could be. Again, we don't know, but people try and have a guess what's well motivated, how might it work. And there's a really popular class called weakly interacting massive particles. These are called WIMPs. And the reason why people really like these as a class of particle physics models for dark matter is that you can really naturally sort of explain the abundance of dark matter that we expect in the universe today, which is about 5 times more than the regular matter. And the way this works is that you have dark matter particles in the early universe. You have the visible matter as well. They're all kind of mixed together in some sort of bath. And you can have that the dark matter particles annihilate into the regular matter, and the regular matter can annihilate into the dark matter. So the process just goes back and forth. And this is in the early universe. And then the universe begins to expand. So we think, the universe started from a Big Bang, it goes out, it gets larger and larger. And as it expands, it's harder for these particles to find each other to annihilate. So what happens is it's expanding faster and faster, and you reach a point where the particles can't find each other. So no more sort of annihilation happens, and you end up with what we call a relic abundance of dark matter. So this is some leftover amount of dark matter, which gives you the amount we see today. Now, if you look at the interaction rate from this process in the early universe to get the right amount of dark matter today, it's actually the same intensity as the signal we see from the center of our galaxy. So what's really surprising about this glow of gamma rays from the center of the galaxy is it actually almost precisely matches this really small sort of interaction cross-section that's actually predicted to give you the right amount of dark matter. So if you were to predict what size should the signal have, it actually has almost exactly the correct signal sort of intensity.
Right.
Which is quite a coincidence, which makes it, I think, very interesting.
And so do we see a similar signature coming from other galaxies?
So people have looked for this. So Andromeda is the one that's closest by. There actually is a signal there too, but it's not clear what's causing this either. So I wouldn't say that it's robust evidence that we definitely have one that matches as well, but there are a number of papers have been written to say, can we compare what we see in the center of our galaxy with the center of Andromeda? And it looks like it can be consistent, but it depends on a few sort of things that you do.
And so if there was a time back near the beginning of the universe where this was happening everywhere, that sounds like a cosmic gamma ray dark matter collision background radiation. I just came up with an acronym there. But so would there be a background gamma ray glow to the entire universe that could be detectable, or would that be sort of hidden behind the cosmic microwave background and so, not visible?
Yeah, so that's a good question. So the way that so dark matter isn't annihilating anymore once it has this point where it's, it expands too fast and this thing isn't happening anymore.
I mean, I guess if it was doing this before 300,000 years after the Big Bang.
Yeah, so it's happening very early in the universe. That's right. Yeah.
Right. And so it would be like blocked by the rest of the universe.
There's also this process is going in both directions. So you wouldn't think about it like, say, in the center of the galaxy, for example, it's just a lot of dark matters there, and it's what's annihilating, giving you these particles. You don't have this sort of thermal equilibrium where it's going back and forth. So it's not quite the same sort of setup.
Right. But I sort of, I think about the early universe where the entire universe was essentially the interior of a star. And it was, it was doing its nucleosynthesis and merging hydrogen and helium. And then it cooled down to the point that it was all just it was opaque. It was like a red glow was the entire universe. And so if this time when the dark matter was close enough to be annihilating, but it's pouring out gamma radiation, that would just be getting absorbed into all the other material that's all around. And so it would be obscured by the early universe is just but I wonder if you had that sort of like, could there be some signal? I guess what I'm asking, because I feel like the cosmic microwave background is the secret to everything. Like every answer that you could possibly want to have answered, it's in there somewhere. And so could you see some signal of this annihilation going on through the CMB or is it just too late?
So yeah, so there's that's yes, that's a really good point. So there are actually constraints that you can set on this process not being too large around the time of when you have this CMB forming or occurring, I guess I should say. So what happens in this case, if dark matter is interacting with too large of a sort of rate, it will then just inject too much ionizing energy into the CMB, and then it just kind of messes everything up and it won't look like how we see. So actually in that regard, you can set constraints on at that particular time in the universe that this rate can't be too large.
Right.
And if you compare the sort of rate you have for the center of the galaxy with the constraints you have from the CMB, they're totally consistent.
Okay.
So the CMB isn't sensitive with the sort of dark matter masses that you need to do this one in the center. So it's not constrained from that point of view.
Right. Okay. Okay. So then, if dark matter is this particle, these WIMPs that are annihilating into each other, does that bring down the 80 orders of magnitude to something more reasonable?
Oh, sure. So this, to actually explain this sort of signal, this is assuming you have something that's around 10 to 100 times the mass of the proton. So we call this like 10 to about 100 GeV for the dark matter mass. So this is you need to have a very specific type of mass to explain the signal. But this is also generally true of these class of models. If you want to naturally have some particle that was in thermal equilibrium in the early universe that gives you this particular weak or small sort of interaction rate, it has to be around, the 10 to 100-ish.
Is there anything else that has that weight, that has that mass? Like, like is the Higgs? I don't know what the Higgs is way heavier, right? Like so
the Higgs is around 126 times the proton mass. So there's W and Z bosons, they're around 80, 90 GeV. There's a number of things that are there for sure.
So definitely within the capabilities in theory of our particle accelerators in terms of being able to have them generated. Okay, well, let's get to the good part, which is using planets and stars as dark matter detectors. So explain this one to me.
Okay, so the general idea or the general setup behind this idea is that, as I mentioned earlier, we have dark matter existing in this sort of galactic halo. So dark matter is whizzing around. We know we have planets and stars just peppered throughout this dark matter halo. So as planets and stars pass through the dark matter halo, dark matter particles can interact with the planets. And if they just scatter off the planet, they'll lose some energy and they can become gravitationally captured. So the gravitational field just pulls it in because it's lost so much energy, it can't escape. And this keeps happening. So over time, you can accumulate a lot of dark matter particles inside these stars or planets. And once you start to really build up a lot of dark matter particles inside, dark matter can start annihilating with itself if it's the type of dark matter that has the particle-antiparticle. So if it annihilates, then it can annihilate and release energy. So there's just some annihilation energy that comes out. And this annihilation energy can be absorbed by the planet. And if energy is absorbed by a planet, its temperature can just increase. So the observable, particularly if you have cold or really old planets, their temperature can increase, and that's what you can look for. There are other signatures as well, which is that the dark matter can annihilate to some other sort of new particle, so part of a dark sector. And this new particle, if it has a long lifetime or it's produced with what we say a large boost, can be just boosted out of the star. So it can travel out of the star or the planet and decay on the outside of the planet to gamma rays or just other visible particles, which we can detect with our telescopes.
I'm sort of thinking of like Cherenkov radiation, the way we can detect cosmic rays as they impact the atmosphere. We don't detect the ray itself; we detect the scatter of particles that have been blasted apart as the particles making its way through the atmosphere. Thanks to relativity, we wouldn't even be able to detect it. So I guess the part that I have trouble with is, like, we've seen in cases of, say, like the Bullet Cluster and other examples where, dark matter, huge clouds of dark matter just seemingly pass right through each other. So what would it take to concentrate dark matter particles in? What would stop them to make them actually fall into and get held into the gravity well? Like if I'm envisioning things could go into orbit around planets, but what would actually put the brakes on them to actually have them fall in?
Yeah, so if they just scatter, so they interact with a high enough sort of interaction rate, they can just lose a lot of energy. Or they can scatter sometimes several times, even thousands of times with the planet, and they will become gravitationally captured. Thinking about the bullet cluster, so the bullet cluster actually, you see it kind of passes through, if the dark matter just passes right through. If you want a dark matter to actually be stopped by this collision, it has to have a really large interaction rate. So really, really, really large. And the sort of ones that we're looking at actually for these planets can be even smaller than what you see in terms of the bullet cluster. So in general, it just means you need to have a large enough sort of interaction rate with the planet. If it's too weak, it will just pass through and nothing will happen. So it doesn't work down to,
Right.
arbitrarily small sort of interaction rates. There's a particular rate that you need for it to lose enough energy and become gravitationally captured.
But the key should really be anywhere you find concentrations of mass, you could very well see dark matter annihilations happening.
Yeah, exactly.
But you say that one way you might be able to detect this is through the planet heating up. But that feels like there's a lot of uncertainty there because we don't know how hot a planet is supposed to be.
For sure. So the way that we can compare to what we would expect to see from a planet is look at, there are some planetary sort of cooling models that exist. And these are based on simulations, so putting in different things like the formation history of the planet, radioactive processes that might happen inside the planet, and looking at just the range of possibilities that you might expect. And you just see how the planet can cool off over time. So what we find in our search in terms of the dark matter heating is really it can be many orders of magnitude larger than what you would expect from these formation models. So while of course we don't know, very robustly everything about all of these cooling models, the amount of dark matter heat is really, really large, to the point where there's just almost no combination of formation histories of other things you could have to expect it to be heated up that much. Now, that said, of course, there's all sorts of anomalies in astrophysics and all sorts of weird things can happen. And, it's very possible that you look at a given planet, something weird happened to it and it doesn't match what you expect. So this is why in part of our search, what we pointed out is, we have something like 300 billion exoplanets in our galaxy. We want to use as many of them as we can, as many of them as we can find. If we get really large statistics, this can kind of help hammer down the uncertainties. So while you might expect, maybe some planets are going to be a bit anomalous, don't act how you might expect, overall, they should be approximately consistent with these cooling models. So overall, we should have a handle on kind of how this works.
So why would planets be easier than stars to use to detect the temperature? Because it feels like checking the temperature of a star is vastly easier than trying to find the temperature of an exoplanet.
Yeah, so that's true. The problem is stars have nuclear fusion happening in their cores, and the amount of heat you're getting from this nuclear fusion is really high. So for at least most of the sort of amounts of dark matter heating that we have, they're not as high as, like, say, the usual sort of main sequence stars, which are really, really hot. The other reason as well is that if you want to try and probe really light dark matter masses, stars like our sun, for example, actually just kick out a lot of the dark matter that it tries to capture. And this happens because the cores are so hot from all this nuclear fusion that the extra temperature gives the dark matter particles kind of like a thermal kick. So they get extra energy and they just get kicked out.
Right.
And if they're getting kicked out, they're never going to annihilate. So you're never going to actually really be able to see the heating, on top of the fact that they're already really hot. So it's a much higher background to have to deal with.
Right. So they're turning into hot particles, which isn't helpful. Okay. So right. And so you, in your most recent paper, proposed doing this with Jupiter specifically.
Right. So what we proposed with Jupiter was to look at the gamma rays. So this is kind of like the high energy light that can come out of Jupiter. So in this case, we didn't want to look at the heating. The reason is if you're heating just Jupiter, it's hard to know for sure if you understand what's going on. As we were just discussing, there's a lot of sort of uncertainties as to what's happening. Really, you want to have like thousands of these planets before you can make some conclusion. So what we proposed with Jupiter is to have the dark matter particles annihilating to some extra like long-lived new particle that then goes outside of Jupiter and decays on the outside and gives you light. So you want to use gamma ray telescopes to look for the light coming from Jupiter that you wouldn't expect otherwise. So that signature is a little bit different in that regard.
And like Jupiter has I think it has a bit of a gamma ray glow from its auroras, I think, doesn't it? And then
Yeah, so there are a few different ways you can get gamma rays just from astrophysical processes. So some are just you can have cosmic rays flying in that are accelerated from the magnetic fields. You can also just have them like passively interacting with the atmosphere. But it wasn't known if you had with these gamma ray, like high energy sort of gamma rays, if Jupiter would really actually emit in those gamma rays at all. So part of what we did that was new with our study also was just to look at Jupiter for the first time in gamma rays. Mm-hmm. So no one knew what to expect. We didn't know what would be there. People have known about Jupiter's existence since, humanity existed, but all this time, no one had looked at it in gamma rays. So we thought it seems like a great idea. Let's see if there's anything there. Maybe there's something new and exciting. Mm-hmm. So we both did that study and then pointed out, actually, if we find some, anomalous sort of signal, maybe it's dark matter. So this is somewhere dark matter might have appeared. Just, Jupiter secretly giving us these particles all this time. Maybe we just didn't know.
So what did
we didn't find anything consistent.
You didn't. Oh, so what did you look at Jupiter with?
So we used something called the Fermi Gamma Ray Space Telescope. So it's a gamma ray telescope, which was launched in 2008, and it's run by NASA. So the great thing about this Fermi telescope is all of its data is publicly available. So you don't actually have to be part of that collaboration to download the data and analyze it. So both myself and my collaborator, Tim Linden, are both experts in using this data. We've used it in different sort of circumstances before. So we then use this to look at Jupiter and do the analysis ourselves.
And how much data did you have on Jupiter? Now,
we had 12 years worth of data.
But wait a second. So there had been observations of Jupiter made by Fermi as it was slewing past, or someone had actually directed it at Jupiter? Or was it just in the field of view?
Yeah, so Fermi sees something like, I think, 20% of the sky at a time, but it's also moving around. So it actually does have a full sky field of view over the period of a day. I think it goes around twice or something like that. So you don't have to point it at Jupiter. So what we did was we just say, well, we know where Jupiter's orbit is. We know where it's going to be relative to us. And we just follow its position around the sky as it moves.
Okay. So yeah, I didn't realize that that's what Fermi was doing. So you just found every frame that contained Jupiter and then gathered all that data together. So what did you find when you observed Jupiter in gamma rays?
Yeah, so we found some interesting things. So first of all, when we looked at just gamma rays that had energies of about a GeV plus, so like the proton mass sort of energy in gamma rays plus, we didn't see any sort of robust excess of what we expect. So we didn't see anything. So nothing was being picked up at all. But then we tried to extend the analysis to lower energies. Now, Fermi's sort of best sensitivity comes from this GeV plus sort of range. So it's better at higher energy gamma rays than the lower energy ones is the point. But we thought we'll try and see, can we see anything with this sort of lower end? And we actually did find a statistically significant excess coming at the very edge of Fermi's possible range. So this is potentially exciting. The thing with this is, though, because it comes from the edge of what Fermi can do, we're really pushing the envelope of what's possible. So it's probably, we think, don't trust at this stage what that result is. So we got the result and we're like, wow, that's really surprising. But then Fermi hasn't even really been checked as to how it performs properly in this sort of energy range, because it's just the edge. No one usually looks that far down.
Right.
So instead, what we said is we have these excellent called MEV gamma ray telescopes, so lower gamma ray energy telescopes that are coming up in a few years, hopefully. And they can look directly at Jupiter and just check, do you see something there as well? And these telescopes are really optimized for these lower energies compared to Fermi, which isn't.
Right. When is one of those due for launch? Because you have to do it from space, right?
Yeah, you do. So I think, the two that I have in mind are called eAstrogam and Amigo. The earliest I think is 2025. The other one I think is later, in the later 2020s.
Are those European missions or?
One is European, one is American.
Okay. That's weird. I haven't even heard of those missions. That's strange. Okay. And so, with that faint signal that you detected in Jupiter, what does that, what, I guess, what does that indicate?
Right. So
If
it
it's
could
real,
indicate, yeah,
which it could very well not be.
right.
Yeah.
Yeah. Great caveat. Yeah.
Yeah. Yeah.
Um, yeah. So if it is real, one, it could be evidence of the gamma rays interacting, so cosmic rays interacting with Jupiter's atmosphere, or again, these ones that have just been sort of re-accelerated in its magnetic fields. So this would be interesting just from an astrophysics perspective because we haven't looked at Jupiter in these sort of energies before. So it would tell us a bit about what Jupiter's atmosphere is like, what its magnetic field's like, and kind of what's going on there. So it could be the first evidence of something like that. It could also potentially be a dark matter signal. I would be more cautious, though, about saying this simply because, at least with the estimates that we did, we think that if you're going to go to such low energies, most of the dark matter probably is kicked out of the system once you get lighter, which is this evaporation process that happens. So you can't go to arbitrarily low dark matter masses inside Jupiter because once it gets too light, even the slightest sort of thermal kick of energy ends up just kicking it out. So you can't see all the way down to really, really light masses. So it's probably not dark matter, but it could be. There could be some particle physics models that somehow, end up giving you dark matter with these lighter masses that could make this signal as well.
I got a question from Six Bob Ohms, which I think is great, which is how does a gamma ray telescope work? Can you explain how you catch gamma rays? Because it's not like a regular telescope.
Yeah, that's a great question. So different telescopes work in different ways. In the case of Fermi, what's happening is the gamma rays entering just the telescope that you see, and then it's looking at electron-positron pairs. So you can have a gamma ray or a photon can then give you electron-positrons as well. This sort of interaction is something that just can happen with the visible matter. And then it's looking at these, reconstructing with these particles. It's looking at the electrons and the positrons and seeing then where everything came from using those. Something like Fermi, also you can't, it depends on what type of telescope you have. So that's something like Fermi. There are other ones that exist that exist actually on Earth. So they're not out in orbit. They look at gamma rays as well. But some of those can't be pointed directly at the sun, for example. So some of them are actually detecting all of these things in different ways. So I think you actually mentioned this before, but some of them, if they want to look at really bright sources, have to look at them indirectly from the gamma ray can interact with the atmosphere and gives you showers of other particles. And it's picking up these other particles and then reconstructing what that would have been given how they find these. So a few of them do things different ways.
It's interesting just how difficult, just how extreme these particles are. And we were covering this actually in Astronomy Cast, I think last week, that there's like a new wavelength of gamma rays that are at the very extreme level. Like they've got a new, I forget the name. I don't know if you, it's like at the most extreme end of the gamma rays. Penta, someone will post it in the chat, I'm sure.
Oh, like PV? Sort of
yeah,
the
yeah.
The PV gamma rays. Yeah, they're very, very high energy.
Yeah.
So there are telescopes that do those. So there's like the Cherenkov Telescope Array can see very high energy gamma rays. There's one called the Hawk Observatory that can do high energy gamma rays as well. There's a few of them. Usually these are the Earth-based ones that just look for the reaction in the atmosphere and the particles that kind of shower after that.
So how does this, I mean, you say you want to do a, like some kind of detection of, do a survey of exoplanets, ideally thousands, hundreds of thousands, millions of exoplanets, try and get some statistical survey. Obviously, it would be pretty tricky to have a gamma radiation exoplanet telescope. You do that through temperature?
So we do it for temperature, but actually, as difficult as this sounds to do with gamma rays, I actually wrote a paper that came out in January actually suggesting this same idea. So looking for these gamma rays coming from exoplanets or exoplanet-like things called like brown dwarfs. And you can actually use this Fermi Gamma Ray Telescope to look for those as well. Because what happens is if you just imagine you have like towards the center of the galaxy, lots of planets or lots of stars, if they're all radiating sort of gamma ray radiation, you'll just see a bright amount of gamma rays coming from the center. So you can detect that and you can look for the gamma rays in that sense.
I mean, I'm wondering, like, could you use this to find, say, brown dwarfs
with the gamma rays.
as opposed to
Yeah,
finding them in the infrared if they're
yeah,
close?
yeah. So it's probably more difficult in that sense because of what we're suggesting with the temperature search, which is the infrared telescope, particularly the James Webb Space Telescope. We don't suggest for James Webb to actually identify the planets itself. Instead, there are other sorts of telescopes that are going to be looking to try and find the exoplanets. So that they use other sorts of techniques called, like, for example, microlensing, which is just looking at light bending around objects, and you can identify, aha, there's something here bending the light. So with that particular search, we're suggesting that, these other telescopes first will find where the planets are, and then James Webb can say, okay, I lock onto that position, measure what is the temperature of this object in this position. So James Webb itself, to begin with, won't be finding the planets in that sort of way.
So I'm going to ask a really uncomfortable question now, which is that, a lot of the researchers, you start with your bachelor's degree, you get your master's degree, you specialize more, you specialize into your doctorate, you're now a postdoctorate. You've been working in a very specialized niche of particle physics where you've ended up in, and a lot of times that kind of informs the range of particles that you're considering, the kind of answers to this question. And I was talking to someone who's researching axions, and she was saying, like, I was really lucky, and I was really interested in axions, and does the particle that you have been trained to look for sort of affect your confirmation? Does it give you confirmation bias for the kind of particle that you think is the most likely outcome to be dark matter? If you could, change horses, would you?
That's an excellent question. And I totally agree with everything that you're saying. I think if you bet on just one particular type of dark matter particle, I think that it can be dangerous in some sense because you have no idea if it's the right one. It could be wrong. It could be ruled out by something. So actually, in general, that is part of the philosophy behind my research, is I try and avoid picking any particular type of dark matter model. Instead, I try and focus more on what are the new search sort of ideas. So what are the different ways you could find dark matter, whether it be really light, like an axion, or something more like these weakly interacting particles that are a bit heavier, or even something even bigger than that. So for that exact reason, I try not to stick to only looking for one type. So I've thought about different types of dark matter particles before, and I'm mostly just interested in, imagine you have some new particle, you don't know what it is. How do you find it using things in space? That is the philosophy behind the research that I do. So I try and focus more on the ideas and think afterwards, what type of models might this apply to? And try not to be tied to just one particular type, because it can be dangerous if you don't know what the right answer is. So.
Well, I think that's really smart that, you're sort of adapting, you're already sort of being aware of what your confirmation bias could be. So I would love to go through some of the other interesting ideas that you've had. I mean, sort of when I kind of imagine sort of the way this works, right? You just think about all the various astrophysical objects that are out there, and then you just try to consider if something is affecting it in some way, we could see something somehow.
Exactly.
So what are some other ideas that you've had in this vein?
Yeah. So particularly to try and have more of an emphasis on the different types of particles and different things that you could see. So one idea that I've been working on that's not published yet is thinking about, we have cosmic rays. They, whizzing around everywhere in the universe. They're very high energy. So they're kind of like having a cosmic collider in some sense. So we already know that with our colliders, like the ones that are based on Earth, like the Large Hadron Collider, for example, we're just throwing together these particles at really, really high energies. And we naturally have things like this out in space, being the cosmic rays. So I thought it's interesting to think about, if these cosmic rays then interact with different objects in space, what could happen? And what could this mean for any sort of dark sector particles? And one thing that could happen is if a cosmic ray hits the backside of the moon, it can then make a new particle that travels through the moon. So it can travel through, if it's just like doesn't interact very much, It travels through and then it can decay on the other side of the moon. And that you would see new particles coming from this as well. And so new particles, for example, could be these gamma rays. So again, you could use this Fermi Space Telescope to look for, the
Right.
moon lighting up in gamma rays.
Have you tried that yet?
It's in progress.
Okay,
So
yeah,
the
yeah.
paper's not out.
Yeah, look at the. Well, I will. Well, I won't tell anybody. Right. So that's cool. So you would have potentially a gamma ray glow coming from the moon that would be explained by particles crashing into the far side of it, and then generating particles through the other side. That's really cool. I like that.
Exactly. So that would be a totally different type of particle. So, ones that are much, much lighter than these, ones I was talking about before, ones that are more consistent with where this axion sort of masses are that are much, much lighter. So depending on what sort of system you're looking at and how the interactions might happen, they're usually more optimized for particular types of masses and particular types of interactions. So that's one that's very different to the other sorts of searches I've been thinking about. Lighter particles, different sort of process.
I sort of think about like the discovery of the cosmic microwave background radiation. It was sort of a similar thing where on the one hand you had a researcher predicting this temperature that should be across the entire universe, and on the other hand you had these poor people trying to clean pigeon poop out of their radar system, and the temperature anomaly that they were seeing was matched by the predictions that were made over here, and then you put those together and get one of the most fundamental discoveries made. Do you have any more of these?
Oh my goodness. More of what exactly?
Well, more of ways that astrophysical objects should behave if there was some interaction with dark matter that was happening. I mean, we could just brainstorm here if you want, but I'm sure you've spent a lot of time thinking about this. I'm sort of imagining like, you take a neutron star and a cold molecular cloud of hydrogen and you put them together and then, so.
Yeah, no, for sure. There's lots of things like that. There's other things you can think about, like if you imagine dark matter is accumulated in any of these sorts of objects, maybe neutron stars. If you have two neutron stars that are, so these sort of binary neutron star mergers, which everyone's looking at, very excited about now with the gravitational wave signals that we can see. But if you think about what dark matter might be inside these as they do this sort of in spiral, they can have what we call long-range forces, which is the dark matter particles can have an interaction, even though they're not right next to each other. So they can have a force between them that as they're spinning in, the dark matter particles and these forces will change how this sort of spin looks when we look at all the different sort of parameters, like the properties of how the spin is going. So there's things like that as well.
Yeah.
There are so many things because there's so many different systems that are, exploding or, merging or colliding. So all of these experiments have already really been just happening. We just have to be creative enough to think about what do we get out of looking at these observables that already just exist. So there's so many of these sorts of things.
I mean, another example I like to think of is like gravitational lenses. Like there were gravitational lenses in astrophotographs for decades, and nobody knew what they were. Nobody even thought that they were anything but a smudge in the glass of the telescope, as opposed to the gravity of an entire galaxy cluster, lensing another object. And so it took somebody to kind of go, we should see something like this. And people are like, well, I've seen a million of those, right?
Yeah. That is the perfect example. Because
it's yours.
So many things.
Yeah.
Exactly.
Put that in your book.
All of these things are, these are just everywhere. We just have to realize what's happening and what we could get out of them. So many of these things are probably right under our noses and we just haven't realized yet.
What do you think about sort of this new realm of more time domain astronomy? Things like the Vera Rubin Observatory coming online, our ability to sort of see the night sky changing. Do you think that will play a role in some of the work that you do?
Oh, yeah. All of this is just so interesting. I think in particular, what we're going to learn very soon is just seeing the universe much further away and much further back in time. So again, actually, we can do some of this as well with the James Webb Space Telescope. So looking, more into the infrared, we can see because, as things are going away, they're redshifted. So you can see a lot of really interesting information that's just hiding around the corner in the infrared. You can also see through dust, so you can see further away, depending on what the wavelengths are. There's so many combinations of things that are going to be very interesting for sure.
The particle physics community is it a bit of a dead end at this point? The Large Hadron Collider found the Higgs boson and then has failed to find all of the particles that would be predicted by supersymmetry and other various competing theories. And so the plan now is to make it better and see if that's going to work. And then the other possibility is to build a super LHC and then just start smashing stuff at random to see what falls out and hope that you've got some answers in the rubble. If you were guiding the teams, where would you recommend as they consider what's the next big particle accelerator?
That's an excellent question. So I think also on thinking about what we got out of the Large Hadron Collider, I think we learned a lot about nature. So apart from, of course, discovering the Higgs boson and learning a lot about how it interacts or doesn't interact, I think it was extremely valuable to learn. I mean, I think my personal opinion is some like models, sort of ideas like supersymmetry probably aren't realized by nature. That's just my personal opinion. I probably don't think that. I mean, it still could be. It just seems the motivation behind all of this now is kind of pushed into a direction that's a bit difficult for me personally to reconcile with what I would expect would happen. But I think that was also worth a lot to the community, because this was, I think, the sort of like the theory that really just hailed as this is the next thing. This will explain a lot of the problems we have and give us all these new particles. So I think learning that most likely isn't true is extremely valuable.
I mean, that's how science works, really.
Exactly. So I think we actually learned a lot. I think it's also important to keep in mind that even when we don't find the things we might think that are there, that's really pushed us in a new direction to start thinking about, okay, maybe that's not right, but what else might be correct? So I think it was very successful in showing us a lot of different things. In terms of the next collider after the Large Hadron Collider, I think it's difficult to say what is the most interesting. I think there are a lot of very interesting proposals. I think people have had very interesting proposals recently about muon colliders. They have a lot of sort of experimental difficulties in actually getting them to work the way we want them to work, mostly just because muons decay. So if you have things that decay that are in your beam, it becomes difficult knowing how to deal with that. So I think that's very interesting, particularly with I guess, as you know, there was this G-2 announcement recently. So that's still holding up. Maybe there's some new physics there. And maybe something like a muon collider would shed light on that. But I'm not sure which one is the best bet. It's hard to say. But there are lots of interesting sorts of possibilities that are being proposed that could be, again, very valuable to the community.
Yeah. I mean, it's sort of, it's come at a really interesting time, and it's sort of, I think it's like 4.2 sigma. So it's definitely a really good result, but I mean, it could still be, it's still only one machine. It could be, there's all kinds of reasons why it could go away. It could be faster than light neutrinos in a couple of years, or cold fusion, if, once the bugs are worked out.
Right.
So if you were to place your bets right now on what dark matter is, and I need less orders of magnitude, what is it?
I can't tell you.
You refuse.
I mean,
okay.
I could choose something if you just like to hear something, but it's completely arbitrary. I still think we have no idea what it is, and it could be absolutely anything. And I think this is the main reason why, for me, astrophysics is so exciting to think about, or things in space. We have these things that just exist. There is probably something sitting right under our noses, and I think having the sort of philosophy of we really don't know what dark matter is. We shouldn't focus on what particle physics model explains what it is. We should just try and think, what is the way to maximize our discovery possibilities? And I think the way to do that is just focus on what new searches can we do with things that already exist just by looking in the sky. So I think that's the way to get to the answer for me personally. but I still don't know. It could
Yeah.
really be almost anything.
It's I find it really exciting. Like I'm sort of make this reference a lot of the time. It's like a good mystery novel that you don't know the ending, and you're sort of
Yeah.
seeing all of the characters, and you're seeing all of the highs and lows and the conflicts and all that,
Yeah.
and you're working towards the outcome, or even better, like watching a sports ball game where you don't know the outcome, and so you're kind of riveted, and the more you learn about the different possibilities, the more kind of skin in the game that you have, how more exciting it is to see how this all will play out. And I guess
Right.
since you provided the most generic prediction, you're going to be very right. So
That's great.
congratulations.
Good way to go.
Yeah, it's something. Yeah,
Uh-huh.
we'll
Yep, it's
find it.
something.
Yeah.
Enjoy.
Do
Yeah.
you and so if I was to ask you when, would you also tell me never?
Sorry, when?
When do you think that we'll have a good answer?
I think we could have an answer in the next few decades. Again, I mean, this is also just a complete guess. The reason I feel more comfortable actually giving some answer for this is that I think really just when like maximizing all the different ways that we can really see things, there are so many telescopes, particularly astrophysical ones, that are going to measure all these systems in a really wide range of wavelengths. And, we're going to be looking
Hmm.
for lots of particles. We're going to be really searching lots of different systems. I think it's totally plausible that we see something. I mean, also, we potentially already have a hint of what dark matter could be right now, which is this gamma ray glow from the center of the
Hmm.
galaxy. That certainly isn't ruled out. That really could be dark matter. And if it is, this was like our most basic prediction from like 30 years ago of what it might be. I mean, maybe it turns out that's it. And then if that's true, then we will already at least have a direction to follow up on of, well, if dark matter, annihilates like this and interacts like this, what other systems do we want to check? Because of course, if you have
Right.
something from the center of the galaxy, you probably won't trust for sure what's going on. So you want to, as you had pointed out earlier, just look in different systems and check, does everything look consistent? So that's totally possible. That could be dark
Yeah.
matter.
But then we would, it's one thing to have a pretty good sense of what it is. It's another thing to actually be able to make them in a particle collider and and know that you actually found the particle. But it is interesting to me that you picked something that is sort of roughly your working career. So,
Yeah.
it's interesting. So,
Yeah.
that could be
That's how great.
that could be the confirmation bias creeping in back again. Well, Dr. Lean, it was an absolute pleasure to talk to you. Thank you so much for answering all of my questions about dark matter. I'm a real fan of your technique of going after sort of these clever places where dark matter could be revealing hints indirectly, and I think if it helps, I think that's the way. I think it's great, and so I look forward to you. I look forward to your Nobel Prize.
Yeah, sure, I do too.
Yeah. Now, if
Thanks
people
a lot.
want to keep track of your work, where should they go?
So I post most of my work on Twitter. I post interesting things that I find there. So you can find me on Twitter. We're the
Awesome.
best place.
And you've got and of course, all your papers are on archive and so on. So if people want to
Yeah, they're
dig
all
into it,
online.
and they're the one on Jupiter was quite readable. I liked it, and so definitely people should check it out. All right. Well, thank you so much,
Thank you.
and good luck with the search.
Great. All right. Thanks a lot for having me. Bye.